Hi, my name is Paul Grenier and I'm a volunteer with the Martin Fleischmann Memorial Project. So you'll have to let me know if you can hear me. I have got a different setup today and we're going to try some technical stuff, so it's going to be a bit different presentation. I've got a little bit of science to talk through with you and some requests for people to go and dig around in the scientific archives. So if people can let me know if they can hear me, that would be great. And whilst people are hopefully letting me know, I am going to try to simulcast to a Zoom chat. And so, okay, so you can hear me, great. So I'm going to try and simulcast to a Zoom chat. So I'm going to copy the Zoom link into the YouTube stream in a minute. And so what I'm trying to do is I'm trying to break test a solution. I've got a whole bunch of different cameras here, and I'm looking to see whether I will be able to do different types of casting for live experiments with multiple cameras, and also for people to be interactive and that to be broadcast simultaneously on YouTube, as well as for those people that find it easier to access at YouTube. And then we can have questions in text on YouTube and questions in facial video format directly on the same, recorded onto the same YouTube stream. So that is a very ambitious thing that I'm going to try to do tonight, and I'd like your help with that. And this might also mean that in the future we'll be able to run very affordable conferences where people can be both physically involved and also they can be online as well. So that's kind of what I am trying to achieve here. So just one would be great, Gordon. Okay. Yeah, so the technical thing, so I'm trying to monitor the stress on the computer and stuff, and so that it doesn't seem so bad on the CPU at the moment. And we are going to be talking about today, hopefully, if this works, and I can switch to it. I'm going to switch the presentation cover slide on. We are going to be talking about now, which one do I want? Oh, I haven't actually got the right one, have I? Well, that's the first thing that's gone wrong, so just give me a second there. I need something with me, which is which one? Which one do I need? I want the presentation on its own, which is there. Is it? I don't know. It is. Give me a second. Give me a second. I'm just trying to fix something here. Okay, let me just see. Is it that one? That one? No. Is it that one? It is that one. Okay, all right. I'm not a complete idiot, although some people would disagree with my assertion there. Okay. All right. I'm in my pajamas, so skip to Zoom today. Skip to, no, I really have to test the Zoom simulcast today. So I'm going to actually see if I can get that link up for you. And then if anyone can join in there, that would be great. I'm going to drop the Zoom chat. Okay. Meetings. Copy invitation. Let's see if that actually works. Right. So this is the link to the Zoom meeting. I don't know whether it'll give me a chance to do the link. Okay, that is the link. And can people, if anyone's there, just see if anyone can join in, we shall see. So has anyone got Zoom? Has anyone got Zoom? Hi David, I'm going to be doing a simulcast attempt to Zoom during this presentation. And so if you have Zoom, you can join in, and maybe you'd like to talk about some of your experiments that you're working on at the moment. That would be great. So there's the Zoom link. I can see, I'm going to see if anyone's asking to come in. No one's asking to come in at the moment on Zoom. Okay. We shall see. Now the question I have is, can I see the Zoom window? And if I can do that, I actually need to add that in as an option. So we'll see. YouTube mic is off or super quiet. Is that the case for anyone? Is it super quiet? I don't know. Audio, maybe I can chuck it up a little bit. Is that a little bit louder? I don't want to clip. It's going into the red there. It says the host has another meeting in progress. Okay, so I'll kill that meeting. That's good. Right. So I'm going to end meeting for all, and I'm going to let me just do a new meeting. Let me do that. I'm gonna. Okay, that's better, is it? Great. Okay, so I just had the audio level a little bit low because I was doing some testing earlier today. Okay, so I'm going to new meeting. Okay, I've started a new meeting. Can you try and join that meeting? Okay. Oh, it sounds crystal clear. Okay, brilliant. Okay. Okay. Can you try? It still says the same thing. Okay, so I'm gonna try end meeting for all. I'll try a new meeting. Sorry. What I want to try and do is to maybe launch the what do you call it? Zoom in the middle or towards the end of presentations, so people can interact with their face if they wish to. So please wait for host to start this meeting. Right, I've not started the meeting yet, so I'm gonna do a new meeting here, and no, I will. Okay. I don't really want to add another tool. Drav Rajput is suggesting Microsoft Teams. I don't really want to add another tool, so if that's okay with you. Okay, so I've started a meeting. So we shall see if people can join. Right. And I'll do that. Okay. Right. So participants. We've got 2 participants. That's probably me and me, isn't it? Oh no, we got 3 participants. Okay. So something happened. Let me just see if I can see anyone. Gallery. 2 people are waiting in the waiting room. Okay, so I'm going to admit all. So I've got Artifact and John Watson joining. Okay, and Dan Moretti, admit. Okay. Right. So Dan Moretti is joining, and what I'm going to do is I'm going to try and capture this stream. Okay, great, Drav. So, like I say, I'm trying to come up with a technical solution that will allow for a range of different options in terms of people participating in things and being able to ask direct questions of individuals, and it going out on the YouTube stream as well for those people that find YouTube much easier to use. Okay, so CPU is still fine, still hitting a decent frame rate. Okay, that's okay. So we are streaming also, and it should be recording in the cloud for that. My concern now is that we're going to get audio feedback. Well, you can, well, okay, YouTube, should you use Zoom or YouTube for audio? It depends if you're going to participate. If you're going to participate, then I would suggest using Zoom. Zoom will be a fraction behind, but it should be roughly synced, and you will get the idea of what's going on. So I have Artifact, John Watson, and Dan Moretti in Zoom. And what I'm going to try and do is I'm going to try and capture the Zoom window into a frame so that we can see that as well. So I can put that on the switch interface. So let me just see if I can do that. I'm going to switch to studio mode so I don't mess things up. And we are going to add another one here, and we're going to call this Zoom. And this is going to be a window. Window capture. Okay, and that'll be fine. It doesn't seem to be showing much, that's the only problem. Okay. Okay, I don't see much on that window, which is disappointing. Okay. Okay. No mic and cam on my PC. Hi there. Okay, so that's for Artifacts, just saying he has no mic or camera. And at the moment, this is what I'm seeing on Zoom, so it's not ideal at the moment. Dan Moretti's connecting his audio. Excellent. We've lost someone. We've lost John. Okay. Okay. Right. So if I switch, you can see that I'm not actually seeing much in my Zoom window. So if I switch, do a transition there, this is what I'm capturing from a Zoom window, but essentially Zoom is receiving the correct video. It should be receiving the same audio that I'm broadcasting on YouTube, so it doesn't really matter. My concern would be when people are trying to call in and we don't hear them, so I probably need a virtual patch there. So I can see Dan Moretti's face, but I can't see it. Hello, I can see you, but no one else can. Okay. Oh, I can even hear him. Can you hear Dan, by the way? So we just wait. Could anyone hear Dan? Yeah, okay, so can anyone on YouTube hear Dan? So I'm... No, this is something I've never seen done before, so... Okay, Artifact can hear Dan, but yes, he's on Zoom, so... Can any... Okay, so you can't hear Dan through YouTube. So I think there's a couple of things that I need to sort out with this, and that is maybe to patch through the audio. So maybe I can add an audio stream in here. Okay, so let me see if I can add one audio channel in here. Sorry, this is not what you were expecting, but we will get on to more normal programming in a little while. No, this is absolutely fantastic. This may enable some really, really nice streams in the future. So let's see if I can pull in an audio here. So is it going to give me anything from there? Well, that's not going to do it, is it? Okay. So, I don't think... try and share the YouTube window with audio also shared in Zoom. The patching from the capture of the video from Zoom is not working correctly. I don't know why that is. And I need a tool to capture the audio back. So I think what I will do, use Google Meets. Yes, we used Google Meets before, but there's a lot of flexibility in Zoom, having used it quite a lot with the Russian community and over the last year or so, that it didn't really have in Google Meet. And maybe it has got it now. But I think I'm trying to want to work with Zoom at this moment because it has this in the cloud recording, which then people can access the cloud recording and download the videos and things like that. So that's the way I want to go. But I believe I'm going to need to patch the audio through somehow. And so Dan, could you do a little bit more speaking? And I'm just going to see if I can. Okay, so I'm on a PC right now. So I have a tool in mind that will do this. It will capture the audio from Zoom, and I'll be able to patch it in as a virtual input to OBS. And I have that tool on my Mac, and I use that sometimes when I'm patching various video through. And in fact, I've already done that when I am patching audio through for people on Zoom during my calls with the Russian community. So I have a solution in mind, and this is proven that it did not work. So thank you very much. I think what I'm going to do is I'm going to cull the Zoom call because I think people can ask questions this time, and I'm just going to resume normal programming for the presentation today, which is going to be a little bit of a shorter one. In fact, as the Zoom is working and I can hear people, I can relay the questions if people want to ask with their face, and then I might be able to composite the two streams at the end of the night, as it were. Okay, so let me go back to the presentation, and I'll leave the people that are already in the Zoom room so that if they want to speak rather than type, we can do that. So thank you everyone for bearing with me whilst we tried this technical thing. I'm not promising I won't try again at some point in the middle of the week if someone wants to help me resolve this, but I think we just got the audio that we need to capture back in to make it work. Okay. Yeah, okay, all right. Well, in that case, if no one's interested in being in the Zoom for now, I'm going to quick kill the Zoom. So thank you very much for those people that helped me find out what the problem is. And thank you very much. Bye. Okay, so I'm not killing those people that are in YouTube. Okay, so where are we? I'm going to switch that back to normal mode, not studio mode. And we are going here. So binding energy. What is binding energy? Well, let's have a look at what binding energy is, and we are going to go to Wikipedia. Why not? And so this is the Wikipedia entry on binding energy here, and it says, in physics and chemistry, binding energy is the smallest amount of energy required to remove a particle from a system of particles, or to disassemble a system of particles into individual parts. In the former meaning, the term is predominantly used in condensed matter physics, atomic physics, and chemistry, whereas in nuclear physics, the term separation energy is used. A bound system is typically at a lower energy level than its unbound constituents. According to the relativity theory, a delta E decrease in the total energy of the system is accompanied by a decrease in delta M in total mass, where this one, which we all know, okay, just reordered, okay? So you may or may not know there is a lot of types of binding energy, and we're going to look at a couple of these for purposes of the argument I want to make tonight. And the first one here is gravitational binding energy. The gravitational binding energy of an object, such as a celestial body, is the energy required to expand the material to infinity. Well, okay, fine. Bond energy, bond dissociation energy. So this is kind of like more like chemical energy, and it's saying the bond dissociation energy of carbon-carbon bond is about 3.6 eV. And I think the highest is something like hydrogen-hydrogen bond, which is 4.2 something eV. Electron binding energy, ionization energy. So you might know when we have our Townsend avalanches, you might need energy to release the electrons and produce ions from a gas, for instance. And this is what we're talking about here in ionization energy. And then we're getting on to, well, the other thing is you might want to create electrons somehow or rip electrons off. So if you had a situation where it says here, among the chemical elements, the range of ionization energy is from 3.8939 eV for the outermost electron in an atom of cesium to 11.567617 kiloelectron volts for the innermost electron in an atom of copper. So there's a very, very large gap between the lowest energy required to remove a cesium electron and the innermost electron of copper here. And so that gives you an idea of what the energy is required to strip electrons from a material. Okay, here we got atomic binding energy. The atomic binding energy of the atom is the energy required to disassemble an atom into free electrons and a nucleus. It is the sum of the ionization energies of all the electrons belonging to a specific atom. The atomic binding energy derives from the electromagnetic interaction of the electrons with the nucleus mediated by photons. And then here we have nuclear binding energy, and this is kind of where we're going to stop at the moment. But this is nuclear binding energy is the energy required to disassemble a nucleus into the free unbound neutrons and protons it is composed of. It is the energy equivalent of the mass defect, the difference between the mass number of the nucleus and its measured mass. Nuclear binding energy derives from the nuclear force or residual strong force, which is mediated by three types of mesons. Okay, and so the average nuclear binding energy per nucleon. Look at this figure here. Very, very important. I'm going to zoom into this, and you'll see why I'm focusing on this a little later. The average nuclear binding energy per nucleon ranges from 2.22452 MeV for hydrogen to, that's hydrogen 2, I guess that is deuterium. Was it deuterium? Yes, deuterium. To 8.7945 mega electron volts for nickel 62. So, my question is, and I've already probably given you the answer, if someone would like to say what they think is the most stable nuclear with the highest binding energy in the periodic table. What is the most highest binding energy in the periodic table? And to help you out, I'm going to have this chart, which we had in he says, I'm going to have this chart, but it's not now showing it, which is not very helpful. It's in the cover slide, but I need to do something. Oh dear. I'm having some issues. So, give me a sec. What is it? Osmium. No, that osmium is the smallest nucleus. Oh, I know what was going on. I wasn't pressing play. Okay, all right. So we are looking at this chart, which was in our that link that you see in red. So I have given you the link there, and what we are interested in is on the left-hand side, you can see binding energy per nucleon. So what that is the total binding energy of the whole nucleus, which is all of the neutrons and protons that are in there, and the energy total divided by the number of nucleons, which is the protons and neutrons. And as you can see, and as you might expect, hydrogen all the way down the bottom of here has 0 binding energy. Now, why has hydrogen got 0 binding energy? Well, it's probably because it doesn't have any other nucleons. So protium, i.e. a proton, as the nucleus of protium, that only has a proton, so it can't have a binding energy between 2 nucleons of the type that we're interested about speaking about today. And you can see deuterium, however, which was the one we saw quoted in our, wherever it went, our document here. It says the minimum for the nuclear binding energy is for hydrogen 2, which is deuterium. And here we can see deuterium. And that's because we actually have 2 nucleons, so we can get some binding energy, and that's 2.2245. Now, what they're giving there is the total. That is the total for those 2 nuclei. And if we go back to the presentation slide here, deuterium is actually showing at 1.1 whatever. And so what they're saying is binding energy per nucleon. So we've divided our 2.2 whatever, and we've come up with this figure of 1.1 is for deuterium. And so if you're able to convert one of your hydrogen in your sun to a neutron and fuse the hydrogen with the neutron and produce, the protium with a neutron to make deuterium, you end up with this increase in binding energy, and you yield energy, and that is your kind of nuclear energy from the mass defect. And if we take tritium, and effectively what we're doing with tritium is we're adding another proton, an electron, and an antineutrino, and we get to tritium, we again have another mass defect, and therefore more binding energy per nucleon. So it's a huge, we go from literally 0 here to 1.1 to 2.8 something for tritium per nucleon, okay? And then we go massive leap up here to this little green spot up here, okay? This little green spot here, which is 7 point whatever. Now that, if you take 2 deuterons, which are 1.1 per nucleon, and you go to helium, then you are getting this massive leap in binding energy, which means you get this massive energy yield from our fusion reaction. And so this is why people try to fuse protium and deuterium or whatever, or deuterium and tritium, or do 2 deuteriums, let's say, for helium, because you get this huge leap in per nucleon binding energy, and that's times 4 in this case. So you get a lot of MeV energy. Okay, so then it drops down, actually. You have to put energy in to get it to drop down to lithium. So really, to get to lithium, say, you go through different pathways, and beryllium 8 decays to 2 for helium as well, anyway, because, you know, it's more stable. And so this is actually an indication of stability as well. And so what did I say? So we've got osmium, iron, carbon. Okay, so actually I already gave you the answer, didn't I? So it's not actually iron. Iron, which you can see right here at the top of the table, if I get rid of my mugshot here, right here at the top of the table, most people would say is iron. And technically it is correct for all of the nuclei in that element, because you have binding energy for each of the different nuclei, and a lot of the nuclei are a nuclei that has a very high binding energy. But in reality, the nickel 62 atom, and if we go back to our Wikipedia article here, it gives it there as 8.7945 MeV for nickel 62. Yes, nickel-62 is the happiest element isotope in the periodic table. And we were told by, I kind of got that from Piantelli in 2015, and I did a presentation later in that year, or the next year, where I talked about nickel-62 being the happiest element isotope in the periodic table, because it has the highest binding energy of any isotope in the periodic table. Now, that means you have to put the most energy into nickel-62 to take it and start breaking it up. And we actually bought, I think it was 1 point something gram, or around about a gram, in I think 2015 or 2016 from a Russian isotope supplier. And I think it was, I don't know, with shipping and stuff, it was about $1,300, $1,400 for 1 gram. I think it was a gram. It might have even been less of that, but it was very little, and it was like buying a speck of dust for about $1,300 or something. Anyway, so and interestingly enough, when we did buy that nickel, when we were talking to suppliers, I think in the US, it was Bob Higgins. He was told by the US supplier that Andrea Rossi had also sought some nickel-62 from them in the past. And it's interesting because when we were with Piantelli, Francesco Piantelli, he said that if you do the Bohr shell radius for many elements, but replacing an electron with a H minus, which is it's an ionized state of protium. That this acts as a sort of very large electron kind of thing. So, and in that case, he's saying that it's kind of like a muon. Now, a muon's, I think, 207 times the mass of an electron. So that produces muon catalyzed fusion, because even at room temperature, it brings the nuclei close enough together in the case of deuteriums that they fuse to helium-4 at room temperature by using these muons. But I think it's about 1,900 or something times bigger. It's much, much bigger, this H minus of Piantelli. And he's saying actually the orbital radius of that in the case of nickel-62 and nickel-64 is such that it actually goes into the nucleus of the atom. And so we chose nickel-62 based on his understanding at that point. And therefore, nickel actually, with the nickel-62 and 64 isotopes, which are a certain percentage, not a lot of natural nickel, they are very, very beneficial if you are to believe the theory of Francesco Piantelli. Now, we have, courtesy of Philip Power, I requested him to put this into the MFMP Parkhomov reaction database as additional data, and you can actually do queries based on it. A number of years ago, I asked him to put the binding energies into the reaction calculator on the show element data. So if we go here to the nanosoft.co.nz, here, show element data, and I'm going to zoom into this so you can see it a little bit clearer. And we'll start with our two, this is our, we got helium here, so helium-4, where is that? Helium-4, so binding energy per nucleon here. So you've got a total binding energy here, and you've got your binding energy per nucleon here, 7.07. And for instance, if we go up to carbon, we can see that that is actually higher for each of the isotopes of carbon than it is for helium. Now let's go back to our chart here that we were referring to. Now, you can see, actually, if I take my mugshot out, that our 4 helium is over here, and our carbon is up here. So again, it would appear that we were synthesizing some boron in our ultra experiment the other week. And given the fact that boron is significantly below carbon, and it's kind of like sideways from here, you would have had to have synthesized some elements in between, or it had to have been in the water already for some reason. Boron is, it's quite interesting to have found that. But carbon, we find carbon in all kinds of LENR experiments, particularly where water is involved. Now, there is the fission process and this nuclear regeneration. And if you are going to do nuclear regeneration, well, carbon is this kind of like, it's this triple alpha nuclei. So it's taking this very stable thing here, and rather than going to here, which and here, this is not beneficial for it to do. The next beneficial element to produce is carbon. You just literally go from here to carbon. It doesn't like doing these things. Okay, so if you're making 4 helium, there's a good reason why, because of the binding energy, that it would synthesize carbon. If you do synthesize 8 beryllium, that decays, I think, in 8 milliseconds to 2,4 helium. So if it does, for whatever reason, start to fuse 2 of these together, then it doesn't want to go down here. It's going to go back and stay at 2,4 helium. But there is a binding energy gain by going to carbon. Not to boron, not to beryllium, but there is to carbon. Now, nitrogen's a little bit hard to go to as gain, because you're kind of going down per nucleon on that. So what is the next element that it likes to produce? Well, the next element is oxygen, and oxygen is the most abundant element in the Earth's crust. Okay, so you kind of start to see why LENR likes to do what LENR likes to do by considering the binding energy per nucleon. It is favourable to produce carbon. It is favourable to produce helium. It is favourable to produce oxygen. And there you have it. You see it there. And you would also imagine that it would be favourable to produce a lot of iron, because it's right at the top here. Now remember what I was saying. Let's go and have a look at a couple of elements by using the Parkhomov reaction database calculator. So oxygen here, we've got 7.52, 7.46 and 7.67. Now oxygen 16, which is this one in the middle here, is not actually, where is it? Carbon 12 here is the most binding energy per nucleon, and out of the 3 isotopes of oxygen. Sorry, oh God, I'll make sense in a minute. Get my worms in the right order. Out of the 3 isotopes of carbon, carbon 12 has the highest binding energy per nucleon, 7.6799. And that kind of would suggest why you get this 98.89. Also, the fact that it's made up of triple alpha, you then kind of, it makes sense that it would produce this first. Okay? All right. And, carbon 14 down here, it's in the tables, but this is radioactive, so it won't want to produce that. And you have to go downhill to produce carbon 13 here. So this is probably when you get a different isotope mixture in the mix. Now, if I go to nitrogen here, what would we expect this to be? We would expect it to be going downhill. So nitrogen 14 here is 7.47 per nucleon. Carbon is 7.67. So it wants to stay at carbon 12 unless it can go to oxygen 16. If you look at oxygen 16, 7.97. Again, this is the most abundant isotope, and you're going downhill in terms of your binding energy per nucleon if you're away from oxygen 16. Okay, now it's not to say that you don't have a higher binding energy overall. So you've got 139 here instead of 127, but your binding energy per nucleon is higher. And so this is why I believe you are seeing this kind of effect, where you're wanting to go to deuterium, you're wanting to go to tritium, but really you want to be going from 2 deuteriums up to the 4 helium. And then the only place you want to go after 4 helium is to carbon. And then the only place you want to go, if I get rid of my mugshot, is to carbon. And then after carbon, you want to go to oxygen. And then this is oxygen so special, as I said before. It is paramagnetic. It likes to grab these pseudomagnetic monopoles. And then you're kind of off to the races at this point. And notice it's kind of like a slope up here, and aluminium, look at it. Aluminium's down here at binding energy per nucleon. But you've got a reasonably large jump relative to the jumps over here. When you go from aluminium to silicon, okay? And so there's a lot of goodwill going up to this iron sort of area up here. Now let's look at the isotopes of iron, okay? So let's go back here and into this. Okay, so so we're going to have a look at silicon here. So our oxygen there, 16 is 7.97. And we go to silicon here, and we've got this lovely, juicy 8.44 per nucleon. Now, the interesting thing about silicon is you do get some higher isotopes here in relatively reasonable abundances. Now, it's 14 Z and 14 neutrons. So it's 14 protons, 14 neutrons. So this is a alpha conjugate nuclei. And so given alpha wants to be made so easily by the fusion process, it's not surprising that the vast majority of this is 92.2% is silicon 28. But because you are actually gaining a little itty squiddly little bit by going to silicon 29 and by a little bit more to silicon 30, there are slightly higher ratios of these two other stable isotopes of silicon. And what is silicon? Silicon is the second most abundant element in the Earth's crust. So if you go back to oxygen, the story in oxygen is you're going downhill. So almost everything here wants to be oxygen 16. In the case of carbon, you are going downhill initially, and carbon 14 is unstable. You can kind of see how carbon 14 would hang about for a little bit of time because of its binding energy, but it does fall apart. So it's got to work a lot harder to go downhill, so you're less likely to get this. Now let's go and have a look at, I think the next one that's really, really interesting for me is calcium, because calcium is again mostly an alpha conjugate nuclei. But you can see that in this case, some of the other isotopes, in fact all of the other isotopes, do have some higher binding energy per nucleon. Relatively, it's actually quite a reasonable chunk of change. Here you're going downhill if you want to go to 43. 43 is not very desirable. We see that as the second least abundant element isotope. This one's a little bit higher than this, but anyway. So my point is that calcium here at 8.55 is really quite high. Really quite high. What do we have in our Wikipedia? In the binding energy here, the nickel 62 is the happiest element isotope in the universe, and that is 8.7945. What do we have here for our calcium 40? 8.55. 8.6. There's not a lot of difference, is there? There's not a lot of difference. So calcium is rudely stable. Okay. Now that paper that we were looking at Mronstev et al. And Sabatimova, they were talking about using isotope 42, and probably it would be similar for isotope 44 and 46 and 48 for producing via a neutrino interaction some dineutrons. So let's have a look at what that was saying here. It's input of a neutrino into your NZX. This is your Z is your proton numbers, the neutron number at the top, and the element. Removes a couple of neutrons, and in this case produces this dineutron, and the the itonic, the iton that then can go on to make the itonic cluster. Helium here is very, very desirable, as we've said. So in this case, you are losing 6 neutrons, you're losing 2 protons, and you're creating 1 helium and 2 neutron. In this case, this is a cluster carbon decay. And so you can kind of get the idea that the helium here and the 12 carbon here are the very desirable, stable products. But the other interesting thing is, in all of these reactions, they are claiming the synthesis of this dinutron. Well, before we go on to the significance of that, let's just have a look at a few more binding energies here. And obviously, we want to look at iron, because everyone says, oh yeah, it's the most stable element. And that is true, element. But look at it. If you look at the binding energy of iron 56 over here, this is 8.7901. Okay? It's not as much, really, as this, 8.792. So there is this particular isotope, which is iron 58, that actually has more binding energy per nucleon. But we've talked about how you can get to iron 56 and iron 54 through various reactions over the past number of years. And you can see here that iron 56 here, now this has got 58, but between them, when you look at 8.7901, the majority of the element is this particular isotope here with this very, very high binding energy. Now, how much different is 8.7901 compared to the where was it? The Wikipedia article on nickel. That's 8.7945. 8.7945. 8.7901. You're into the third decimal place now. I know it's mega electron volts per nucleon, and you have 56 nucleons in here, so it's quite a lot. It's 492 here. Anyway, so there we go. That is that for iron. And then if we go to nickel, we can see, so hold that in mind, that you've got 8.792 and 8.7901 nickel here. Here, if you go to nickel 62, this is 8.7943. Now, is that anywhere close to what we're saying here? 8.794. Okay, so there's a slight variation between Wikipedia and the data that was used by Philip Power to construct this table. But this is the most happy element isotope in the periodic table. However, it's only 3.66% of the mass of nickel. Most of nickel is 8.73. And so, elementally speaking, iron is the most stable element, okay? Because most of it is at 8.79. And so the averaging of the binding energy per nucleus and the binding energy, the average of the binding energy per nucleus is higher for nickel per nucleus, nucleon. And but in the case of nickel, the isotope nickel 62 is actually higher on a binding energy per nucleon. Okay, so now, why have I kind of like made some big deal about the fact that we're always seeing this 2n here, and what is the significance of that? Well, I'm going to draw your attention to a couple of things. So the first thing I want to draw your attention to is this. This is a slide. It is when I'm showing it to you, for some reason. This is a slide from my second presentation at ACC, which was on coherent matter traveling waves, part 1. And it's shoulders making an exotic vacuum object, EVO, and what it is, right? And this is taken from rexresearch.com/EV/EVHTM and rexresearch.com shoulders EVO archive HTM. Any spark has an EVO running out in front of it. An EVO also can be conceived of as an atom without a nucleus, or as a spherical monopole oscillator. EVOs exhibit soliton behavior with number densities equal to Avogadro's number per centimeter cubed. These non-neutral electron plasmoids contain various levels of binding energy which exceed that of atoms. This is the important bit. I tried to draw people's attention to this at Sochi. These non-neutral electron plasmoids contain various levels of binding energy which exceed that of atoms and allows for new types of reactions with matter. Now, as we know, we can create neutral EVOs as well. So they're saying these non-neutral ones, these are because these electrons, so forth, but they can get down to a charge of -1. So just like I was saying with Piantelli, and he's creating this H-, that is acting as a composite particle like an electron, and that is so dense that it doesn't just get close to the nucleus and draw an atom nuclei closer together to fuse, for instance, in the case of room temperature, in the case of muons with deuterium. It's able to get inside the nucleus of nickel-62 and 64 because it's much, much bigger even than a muon, and it's posing as a virtual fermion. And it's actually going down the electron levels, and it's going and actually ends up in the nucleus. And so he says that can cause a change in the atomic number, or it gets ejected out at a very high speed. That was his explanation. And so in this case, if you can imagine something that's acting like an electron and it gets captured into the matter as an electron, then it would be vastly bigger if it kind of disrupts in a certain way, that it would cause maybe all kinds of odd nuclear reactions, particularly if it's carrying a lot of nucleons in there and shielding their mass and charge. All kinds of weird things could go on, and this is apparently, it would have seen what we observed. So these non-neutral electron plasmoids contain various levels of binding energy which exceed that of atoms. Now, here's the first thing I'd like people to try and find, because I don't actually know where this is. What are the binding energies which have been attributed to exotic vacuum objects? Maybe in one of Shoulders' papers, or in his book or something. I don't know, actually. So this is my first challenge to you, is can you go and find out what binding energy an EVO can potentially have? Because he's saying it exceeds atoms, and for it to exceed atoms, we know that it needs to exceed, well, if it's to exceed all atoms, it needs to exceed this, which is the binding energy of nickel-62, down here, nickel-62. It needs to exceed 8.79432 per nucleon in nickel. Okay? Right, so that is the binding energy per nucleon compared to, if I and I need to get rid of this, and it's not doing that for me, and I need to do that, and then no, it's still not doing it for me. Right, let me try it now. There we go. So yeah, so this for me is very, very interesting, because he's not only saying that it exceeds the binding energy of atoms, this allows for new types of reactions with matter. Now, the second one is this low energy neutrino candidate for a particle of electromagnetic substance. I was talking about this in my last presentation last week, and he is talking about these cold neutrinos, but and this plays a role in these type of reactions. But the interesting part about that was in Morozev's work here, where he's talking about these different reactions, and he's talking about the deuterium and palladium reaction and so on. You come down here and you get these various reactions here. But it was about the binding energy. And I kind of, my ears pricked up as I kind of was saying it. I was saying, what? Seriously? So here we go. Conclusion. The most controversial are the following problems. I'm going to zoom into this. The existence of a neutrino component of the matter, the ability of low energy neutrino to initiate nuclear transmutations, and the existence of stable dineutrons. Many researchers made attempts to find stable dineutrons, but they failed. And this is 15 down here, D.V. Alexandrov and so on. The experiments aimed at discovery of stable dineutrons were based on outdated estimation of bound energy. Outdated estimation of bound energy between two neutrons in a dineutron. Listen to this. According to these estimations, the bound energy between two neutrons in a dineutron was assumed equal to about 3 million electron volts. That, as we know, because I've taken you through it, is below many atoms in the periodic table. New evidence shows us that the bound energy between two neutrons in a dineutron amounts to about 22 MeV. 22 MeV. The system, I maybe didn't emphasize that enough in last week's presentation, but anyway, the system of quantum states in a dineutron was studied in reference 6. The first and second quantum states with energies of 3.6 and 11.6 MeV respectively were discovered. Okay, what does 22 MeV mean? So this is reference 16, so I think everyone needs to read reference 16 here. And by the way, this is from 1998, so we're talking about 23 years ago. This was established. 22 MeV. Let's have a look at our chart again. 22. Well, we know from our friend Wikipedia that the nickel 62 here is 8.7945. And here, if we go to nickel, we're seeing here nickel 62 is 8.7943. Okay, so pretty good in agreement there. But this is 22. 22. So what does that mean? It means that it's per nucleon, that is 11. 11, even with basic mass, is well off this chart. It's well off this chart. Yeah? So a dineutron is more stable per nucleon. Its binding energy is higher than every element isotope in the periodic table and probably out to infinity. It's the most stable non-atom kind of atom that exists. And it's neutral. So it can go into nuclei and do weird stuff in the nuclei because it's neutral and they're two neutrons. It just goes in there and makes it a bit weird. Now, at C.I.C, Bill Collis was proposing, you can go and see his paper, which will be published soon, but you can see his presentation and he walks through a number of different experiments, and he thinks about this particle, which he says is a massive particle and that it is neutral. And he says that when he was examining recently, because Piantelli was dismantling his lab, and I've got another story to tell you about that at another time, but he was referring to this very famous rod. I had the pleasure of holding it myself, which produced their most excess heat in the 1990s between him and Focardi. And this was because it was ejecting these protons and they were interacting with the vanadium-50 in the steel and so forth. He did say that he was using lithium and that he never disclosed that until his last patent series. And he had always been using that, apparently. But, you know, if you don't say it, then, you know, can't be blamed if you later claim it, okay? Anyway, so there was lithium in there, but that putting that aside, what Bill Collis, who is the head of the CMNS group, who organizes the annual or semi-annual conferences for the condensed matter nuclear science group, and that was what the C.I.C conference was. He's saying that there's a neutral structure. It's very large. It might be like the Urzion of Yuji Bajatov, and that is sitting on that nickel, and that was transmuting material over a long period of time. And in fact, I think it was about 2 weeks after the nuclear authorities came in and kind of like dealt with the lab after this high energy event, and then returned this rod, and he put it into a cloud chamber and saw these tracks coming off. And you can go and all see this actually in Bill's presentation from Azizi, that he established the high energy of the protons coming off, and that gave him the idea to use these high energy protons to interact with secondary materials like boron or lithium and to produce excess energy that way. And he is saying that what is going on is there's this huge neutral structure in there that is transmuting the matter on a relatively consistent and continuous basis, and that is not too dissimilar, I have to say, and maybe I can find it. Let me find it if I can. It sounds a bit like, I have to say, if I can find it, like the work of S.V. Adamenko, where he observed this black spot that was absorbing his primary ions. So I don't have it there, but if you go and look at the first time I talked about that, really was in my Sochi presentation in 2018. But basically there's this structure on the accretion disk from Adamenko's electrical discharge, and he found that in fact I have it in my monopole clutch video, so I think I do. Yes, I do. Here. So here. So he was finding this structure which he couldn't determine what it was, and he was using a secondary ion mass spectrometer, and this is where you fire into the sample an ion at high energy, and that kind of ablates the atoms in there, and you have a time of flight or whatever to assess the elements that element nuclei that have been knocked off. And he found that he didn't see any of the primary ions, but he also didn't see any of the secondary ions. What happened was they turned off the device, and on the phosphor screen they saw this glow which decayed exponentially. And so they thought, oh, what is it doing? Well, it would appear, to cut a long story short, and I've talked about this before, that it was eating the primary ions. So whatever was happening, the ions were going in, they weren't bouncing off, they were going in. So it's another scenario of are you bringing Muhammad to the mountain or the mountain to Muhammad? In this case, you have a neutral structure that's locked into the accretion disk, and you're firing a charged particle at it, but it doesn't interact with this structure as it goes into it, because the structure is, let's say, neutral, and it consumes that nuclei and then does some nuclear decay to it. Now, the other argument I've made in the past is that this is a pseudo monopole, and it's sitting there, and as the material comes in, it has the forces unified in its core, and as it comes in, it just gets pulled in, and it has a decay, and so you're seeing what would look like a black hole. And so the suggestion is it's something like a black hole, and maybe actually black holes are something like this. They are a plasmoid that's in the structure of a pseudo monopole type structure, or a cluster thereof, and that is consuming the matter and causing it to decay into light and leptons. And so you see this exponential decay here. And so what you might agree then is that this has a higher binding energy per nucleon than the matter that's being thrown at it. So is that what is going on? And is it a cluster of dineutrons? Is that what you're seeing there? Well, there is one other atomic structure that has been proposed, and it's by, again, the Russian community. Now, it's called TH2, which is dark hydrogen. And for those that are Mills lovers, this would be something akin to that. And what they believe in Russia is that it's like this. You have two electrons in the center, and they form a Cooper pair. And I think it's called a Barutz atom or something. And after the person that originally proposed it, and I think it was a long time ago. And so you have this Cooper pair in the middle, and then you have two protons on the outside. Now, other than the lack of antineutrinos here, what are we actually looking at here? Well, you've got two protons and two electrons in an overall structure that is neutral. Okay, so that means it's kind of like a dineutron. And in fact, last Wednesday, the Russian community were discussing this neutral structure that was being proposed by Bill Collis, that is doing this transmutation. And at the end of that presentation, which was Klimov was reviewing the work of Bill Collis and his suggestions and his calculations and so forth. At the end of that, Zatelepin came in and said, well, of course, this is like the Barutz atom, this dark hydrogen. And this, apparently, the dark hydrogen has some interesting properties. And so what they're saying is that because these aren't just two neutrons stuck together, that you have a Cooper pair in the middle, and this is like a superconducting structure in the middle, okay, that this is neutral overall because of its scale, because of it, the 100 femtometers, 8 femtometers, the scale is small, but because you have this Cooper pair, this superconducting structure in the middle, it actually has a magnetic moment, and it gets aligned. And if you go through this presentation, and I've talked about this before, they're talking about how this occurs in here, and they're talking about how these things can form strings and so forth. It's worth going through this presentation with Google Translate on, or maybe the auto translate, because I think that will work, the closed captions, and you can change it there. But here's what they're saying is that these can form into strings and they rotate, and potentially this is what causes strange radiation in their view. And so they have a mark here on some material. If YouTube will update now, because I'm doing the streaming at the same time. Oh dear, come on. So we've got these different tracks here, and they've actually got a bunch of magnets here in a row, and they're saying that it forms these magnetic strings, and that's about that really. But anyway, so this is this, I think it's called a Barutz atom. I'll clarify that. But so there you go. So essentially, what I've been going on about here is something that is neutral, expresses some weird electrical and magnetic properties, can cluster together, which this fulfills that. And if this is effectively this dinutron type structure here, this 2 neutron, because it kind of is, it's like it's 2 electrons and 2 protons in a particular type of atomic structure. If this is something akin to the dinutron, and it has this magnetic properties, electrical magnetic properties, and this intense binding energy, which is outside of the realm of normal nuclear matter, then you could argue that this is absolutely unique. Nothing comes even close in our universe in terms of binding energy per nucleon. I don't think you will ever get anything more than this. And that's it. That's the end of the story. It's not going to be more than 11 million electron volts per nucleon. And so, as was said in the presentation that I gave at ZZ, when you have when you have something that has binding energy exceeding that of atoms, this allows for new types of reaction with matter. And that's basically it. That's basically it. So dark hydrogen, they could be right about it. Is that the dinutron? Is that the dinutron? It could be. And if this is very stable, I mean, this structure here is what Zatalepin in his strange radiation detector is saying was the foundation for them developing that strange radiation detector. So if you remember, it's like a square plate of nickel, very important, because it's magnetic, ferromagnetic, and then he put alternating pole magnets on it, and then he had that on a string. And when he loads his nickel hydrogen reactor, it's up to temperature. He throws the hydrogen in there, fresh hydrogen, into the reactor with the what do you call it? So the PNKO2 carbonyl nickel, and it chucks out this radiation, which he calls the strange radiation, and then that causes this thing to spin round. And so he's saying it's because of these things and the fact that they have this magnetic property. They are neutral, but they have a magnetic property to them. And you can imagine that if these are magnetic, that they could cluster and form a magnetic core. And so we've talked about the magnetic core potentially being stimulated by using oxygen, which has a very high binding energy in that lower part of the table. And that this can pull in these things which may cluster themselves to a kind of a magnetic monopole structure. So you end up with something that's very magnetic as the core, and then the electrons are being pulled in to that Sussex cone to the center. So what I'm laying out here is something potentially that could be going on, which is a little bit more down into the nitty-gritty. And so I think people would need to look at the work that I've shared already about the Baruch, I think it's the Baruch atom, or what they call dark hydrogen, and what this scale, this 100 femtometers, this 8 femtometers scale is relative to other things like other types of special types of hydrogen or ultra-dense hydrogen that people like Homlid are talking about, and how that compares, and also what Homlid is claiming for the binding energy of ultra-dense hydrogen, and what Mills is claiming for his dense hydrogen state. And you know, dense hydrogen was observed and claimed to have been captured under an SEM by Matsumoto, I think in 91 or 1992, and I think he's the first person to have captured this type of matter and called it for what it is. But he says it's itonic hydrogen, i.e. you've got the itons and this 2n. Now how would 2
two neutrons be classed as hydrogen? Well, it isn't really, unless it's kind of something like this dark hydrogen. And if it is this level of stability, 22 MeV, then you could actually see magnetically connected together frosts and potentially crystal structures made out of this dark hydrogen. And there you go. So I will clarify the name of this. I think it's called Barrett's atom. And I think it's a long time ago that this was proposed by, I think it was a Russian guy called Barut. Anyway, so I'm a little bit vague on that just off the top of my head. And that's really what I wanted to talk to you about today. Binding energy and its potential for stimulating nuclear reactions in novel ways, and its relationship to itonic hydrogen and itonic clusters, which are supposedly the same as ball lightning in the work of Matsumoto, and how that connects through to the claims for exotic vacuum objects in Ken Shoulders, and how the binding energy exceeds everything in the periodic table per nucleon. And we started out by talking about how hydrogen has no binding energy per nucleon because it has no other nuclei in there, nucleons in its nuclei, but that for helium is very desirable to go to, and that's what we're trying to do in fusion. And then we jump to carbon because everything in between is a lower binding energy per nucleon. That's another reason to do it. And then we jump again to oxygen because nitrogen is again lower binding energy per nucleon. And then we've got a big leap up to silicon. So silicon and oxygen, most of the Earth's crust. And then up to iron, which is and nickel, which is the Earth's core. And when you start looking at this, everything kind of starts to make sense. It starts to make sense. And dark hydrogen, you could understand how it could interact with material in odd ways. So there we go. That's about what I have to say today. So does anyone have any questions? So yeah, my question for you guys is what is the binding energy and the scale of Mills hydrino? How does that compare to the Barut model here, this dark hydrogen model that they consider in the Russian community? And you know, how would hydrogen with an electron at a lower orbital state, how would that present highly magnetic nature? I don't know, you know, you tell me, but I can understand that this particular atom could have this magnetic nature, which would account for some of the bizarre magnetic anomalies that you see in LENR processes and so forth. And the Matsumoto really was the first to actually take pictures of it. I don't have his book right now, but I've talked about that in the past. So, Pyroman Dan, shouldn't there be a ways to check for interaction to determine which kind of energy locus you're dealing with, i.e. dinutron versus interacting dark hydrogen? So, strictly a dinutron, which you would imagine is two neutrons that are basically, for some reason, right next to each other, which, you know, they're neutral, but you would wonder why they don't decay. And so it doesn't make so much logical sense, whereas this kind of makes logical sense. You've got this in this structure, and it's basically like hydrogen. It's not like, you know, it's like deuterium, in fact. It's like deuterium. And so it has one neutron, which is one electron and a proton, and it has one proton, and then the electron on the outside. So that would be your normal hydrogen, monatomic hydrogen. Okay. But instead of one of the electrons being on the outside, both of the electrons are in a superconducting state, so that they're effectively a wave torus in the center, and they have captured the two protons, and so they end up being effectively a dineutron. So, hey Bob, could dark hydrogen be negative charge electrostatics? Negative charge electrostatics. Well, it's neutral. It doesn't have a charge. That's why it can fly out of your metal reactor, but it magnetically interacts with the Zatelepin, what he calls a strange radiation detector. Yeah, it's the same energy. You could argue that. So if you go and look at Moromstev's work here, let's just see if you can see what I'm seeing. Okay, in Moromstev's work, the most basic one here is whatever atom it is, you're losing two neutrons. You're putting a neutrino in. You're taking two neutrons out. And you are ending up with two neutrons and an iton. And the iton is a positron and an electron bound with a neutrino. So the neutrino is inside of this IE. It's gained an electron, and it's gained a positron. So it's basically caused charge separation in here. And I think the electrons are the same. You've still got the electrons inside this. So the neutrinos basically stimulated the production of an iton and the dinutron. My question is what's happened to the antineutrino for both of these neutrons if it is and maybe that's where you're getting this splitting come from. So it's a bit weird to think about it. I need to think a little bit more about how this comes about and if it leads to the production of these. Because normally when you have a neutron decay, you would have an antineutrino coming out and an electron. But there's only neutrons taken out of here. So there's no electrons captured and there's no antineutrinos. But we're getting a neutrino here, so I just need to think about that a little bit more and to see what the cross correlation is here. It doesn't immediately sit very well. Isn't two protons helium? No, it's two neutrons. In this case, it's effectively like a dineutron, because well, two protons is effectively like helium. What you're looking at here is like helium-2 rearranged, or you're looking at deuterium rearranged. So it's kind of like, but it's neither, because the arrangement is a superconducting structure in the center made out of a Cooper pair of electrons, and that's very stable, and that is expressing a charge which is keeping these two protons in play, and they're spin aligned. So you've got your one electron's pointing down, your proton spin up there, and you've got your electron up here and your proton down there. Okay, so rather than deuterium, the question is, if there is no if there's no neutrinos here, then it's kind of like it's not any of the above. because if it was 2 protons, okay, so there would be no neutrinos there. So it is, as you say, a bit closer to 2 helium, but there is no 2 helium. 2 helium doesn't exist. So it's kind of like 2 helium. Yeah, it just doesn't exist. So, yeah. Yeah, for it to be kind of like deuterium, you would need the antineutrino and this electron to be inside this proton with the antineutrino, and then you would have a proton and the electron orbiting around. So yeah, it's kind of like a reorganized 2 helium. Yeah, it's definitely a new type of matter. And when I say it's new, like I say, I think it's a long time ago that Baruch proposed this, very long time ago. And the Russians are pretty much, many of the Russians seem to be fairly settled on this. Chizov, who's doing this presentation here, it took him a bit of time to, you know, accept it, but he's full on board with it in this presentation. Yeah, I believe the way that this is formed is that you've got an alternation here. So you've got a proton with a spin down and a proton with a spin up, and so you can imagine. Let's talk this through. And this is really another presentation about how generally cold fusion, I believe, works when you're talking about thermal. But in fact, I have a whole experiment that I need to make next door to demonstrate this physically. But essentially, if you've got your ferromagnetic material, and I've talked about this, I think, first in my monopole clutch video. But imagine you've got your ferromagnetic material. Let's call it nickel. Nickel's good at disassociating hydrogen, okay? So what you do is your nickel is at the temperature at which it's able to disassociate hydrogen. So you've got atomic hydrogen. If the atomic hydrogen is split and the electrons move into the electron C on the nickel, you then basically have protons with their small magnetic dipole magnetically attached, adsorbed rather, to the nickel substrate. And then this is the key. This is the absolute key, and I will do it with many different examples. But what Piantelli told us to do was to go as fast as possible, once you've got all this adsorbed hydrogen with the electrons in the sea of electrons, is to go through the Curie point of nickel as fast as you possibly could. Now, why would you want to do that? Well, you would want them to the magnetically bound protons to come off at exactly the same time. And what's interesting is the Curie point for a ferromagnetic material is a very precise thing. And if you come off at exactly the same time and exactly the same temperature, which is the Curie point, then you have them all at the same de Broglie wavelength. Both the electrons and the protons. And what does that give you? It gives you a perfect scenario for the formation of coherent matter. What is the coherent matter in the center here? It is the Cooper pairs. And then you have these of the same wavelength. So it naturally would form this structure. This is what is in the Lockheed Martin patent. You're trying to cause the electrons to come off of a spike, and that allows them to have largely the same phase and largely the same energy. Then you put it over a magnet, and the magnet assists with the coherence, and you produce the coherent matter wave. Here you are releasing it at the same time. This is exactly the same. So let me go to here, and I'm going to remote view. In fact, I'm basically telling you in what I'm saying now, this is probably one of the biggest revelations. I know I've kind of said it. I haven't said it this precisely. I did say it in my statements to Francesco Celani here, which you can't see. It's this presentation here. I verbally said it to him because he deserved to hear it first. But essentially what you are doing is a very, very simple version of what was proposed to the Linear Accelerator Forum by Matsumoto. So Matsumoto is saying, use a LINAC here to, this is a linear accelerator, to accelerate your protons to exactly the same energy. Bunched protons with high energy, but more interestingly, with exactly the same energy, okay? Because you're doing it in an accelerator. And then what you do is you create bunched electrons with high energy. What do bunched electrons do? They force coherence. What is coherent electrons? That is Cooper pairs, right? So you have Cooper pairs coming in to electrons, to protons with the same energy. What I'm telling you here is that is what your magnetic material is doing when you've got your small dipole protons, atomic nuclei of protium, or your deuterons on your nickel with their small dipole, magnetically adsorbed to the nickel. There are electrons in the sea. All of the electrons are at the same temperature. All of the protons are at the same temperature. And they're all there, and you release them instantaneously. You have them the same de Broglie wavelength, and you have them in phase. And if you've got little cracks or you've got little tips, then you've got a better chance of all those things that I talked about from Messias. All of those ways to produce ectons. That you have a higher chance of bunching, and therefore you will get the production of itonic clusters in the same way effectively, but without all of the extremely expensive equipment that is being proposed here by Takaaki Matsumoto. And so I would suggest that if you were to want to do this better, you would choose iron or gadolinium. Nickel's good. Nickel's good. It is, because it can easily do the dissociation and of the hydrogen itself, the atomic hydrogen. The other one is cobalt. Cobalt's good from the point of view that it has the highest Curie point. Okay, but you could also use other elements, combinations like samarium cobalt. And in fact, I think I think it was ICCF 5 or some very early ICCF, there was a guy in Hawaii where this was being presented, and he used samarium cobalt. It was crushed up samarium cobalt magnets, and he was putting deuterium in, and he was claiming huge amounts of excess heat. But because he was a little bit off the wall, they wouldn't let him show it. But Martin Fleischmann was very, very interested. But the samarium cobalt, that is a magnet with I think it's got a very high Curie point. And so it not only has the ability to do the what I'm saying is causing these itonic clusters, or the strange radiation, or the precursor, or what leads to the magnetic monopoles, which is part of the whole story of itonic clusters and ball lightning. It has all of the things there. Plus, it has samarium. And samarium has quite a few isotopes that like to decay in this mode through alpha cluster decay here, and probably would lead to carbon cluster decay. So samarium cobalt and deuterons, using the talk about down here, with the deuterons doing what I'm saying, and I think he was cycling it. And that, my friends, is what we were doing in October 2013, when we had the nickel copper Constantan wire of Francesco Celani, and we saw these radiation pulses, which I believe now were not gamma, as we called it at the time. They were emissions of strange radiation. And what is strange radiation? It is these itonic clusters. What is the itonic clusters? Potentially, it is this material here that we are looking at here. Okay, so I'm going to give a huge thing away right now. This for me is the big giveaway of today. Mats Lewin. I'll step one back. When we were with Francesco Piantelli in 2015, he was talking about this nickel 6264, which I've talked about in this presentation so far. Oh man, you're going to love this. You're going to love this. It's just so mind-blowing. And Piantelli was talking about 6264, and then he said, but there's one element on that same periodic table that's even better. Even better. And he left something on the screen, but he didn't refer to it. It was like he's trying to give a clue, but he's not actually spelling it out. He's not actually spelling it out. Then I was talking to Mats Lewin a period of time later. And this was after Sergio Ficcardi had died. And I was recounting this situation. And he said, well, that's very interesting. I'll tell you why. He says because once Francesco Piantelli sent a sample of what he said was nickel to Ficcardi to test in Ficcardi's reactor, and said, look, see how this works. See how this works. Just follow the normal protocol. See how it works. And Ficcardi looked at it and whatever, for whatever reason, he decided to look at it under the SEM. And he found out that it was the element that was on the screen that Piantelli left on the screen when we were with him, when he was talking about an element in the periodic table that's better than nickel. And that element, my friends, was iron. Straight iron. The same iron that was in the 1992 debriefing paper from Soviet energetics people from the CIA that was declassified a number of years back, which we had on our MFMP Facebook page, where these Russian scientists were saying, yeah, we can use 1 kilo of iron to get to Alpha Centauri and back in 12 years. And the method that we use to extract the hidden energy within the matter is also the same technology that provides the propulsion to get us there. Now, what I've connected you to there is the fact that iron is ferromagnetic. Well, it's pretty damn ferromagnetic. Now I'm going to tell you something else, my friends. So, Mats Lewin does not know what I've just said there. This explains why Piantelli sent that iron sample and asked very seriously to Ficcardi. But when Piantelli was with us, he told us there are things that Ficcardi doesn't know because I've not told him. And so he could not have told Rossi. He could not have told Rossi. And I believe that this is one of those things. That iron worked just as well. Just as well. Now, what is going on in the LEC experiments that MFMP volunteer and co-director Alan Goldwater has just replicated, these Frank Gordon experiments, they are using iron. Now, I'm going to tell you something else right now. I sat down in the foyer of the Azizi Hotel with Bill Collis, the head of the Condensed Matter Nuclear Science organization. And he was saying, oh, it's sad, I was with Piantelli when he was taking down his lab. And you know what? He was giving things away and he said, do you want this? Do you want this? Do you want this? And he said, he gave me this huge sheet of metal. And I said, what is that? And he says, it's gadolinium. Why would Piantelli have a sheet of gadolinium? I will tell you that I think that he knew the importance of magnetism to the Leonard process. He hadn't said it, but I believe that that is true. Either he was guessing, I don't know. But I think he was onto it. The fact that in the 1990s he gave that ion to Focardi. Focardi thought he was being taken for a ride. I don't even know whether he actually ran that. I need to check with Mats Lewin. But he thought he was being taken for a ride. But I think, no, Piantelli was deadly serious. And I can tell you that you're hearing this first for the first time, because he didn't know, Bill Collis did not know that gadolinium would be working in this way, and there would be a very specific reason that he had gadolinium. Now, gadolinium has this fantastic neutron absorbent process. And I'm going to tell you something else now. When I was in Russia and we tested at Synthestech the MFMP's Hutchison sample 18 coral twist, and we found that the nickel 61 isotope was 3.7 times natural ratio on this octopole mass spectrometer, and that the lead 207 was 70%, I believe, in excess of natural ratio. So your two fermionic isotopes there were higher than natural ratio. These are synthesized elements on the aluminium from John Hutchison, and they are higher than natural ratio. So something has gone on which is non-natural process. And I believe that it's because they're fermionic, they get kicked out, and so on. And the 61 observation was observed recently and presented by Savatamova at ICCF 23 in China. I said that this is an astounding finding. And he says, well, that's nothing. And just give me a second here. I just need to check something. I was talking to him about the importance of neutron absorbers, whether that's cadmium, cobalt, cadmium, boron, indium, gadolinium. Anyway. He said, that's nothing. He said this. He says, my gadolinium has absolutely 0% gadolinium 152 left. Absolutely 0. So I thought, I bet that's an unstable isotope. So I went straight upstairs and tried to find out. And sure it is. It's an alpha decay isotope. It's an alpha decay isotope. It's only at 0.2% in the crust, but these octopole mass spectrometers are very, very sensitive. So it had completely removed this isotope. There was no detectable isotope 152 in there, and he was absolutely amazed. Alpha decay isotope. Look at our samarium. I've just been talking about samarium. Look what we have in samarium. We have 3 isotopes which are alpha decay. We have one which is 11.24%. We have another one which is 14.97%. So nearly 1/4, over 1/4 of all samarium is an alpha decay isotope. What is that? What are they saying is likely to occur here? We will have alpha cluster decay. Now, how would your tungsten decay here? If we had tungsten, well, we have an alpha decay isotope here, and it's 2.5. Sorry, what is it? It's not a lot, but you've got to remember that this is all through tungsten. So could that be part of why you see tungsten disappear when you get interaction with potentially this Berute's atom, this dark hydrogen, or strange radiation in general, or itonic clusters here, and you get this alpha decay triggered? Because all through that tungsten is this alpha decay. And once those alphas are coming out at 2.5 million electron volts, the whole system gets highly energized and it's a nuclear reaction. It then starts cascading. Is that why tungsten is, in my opinion, the fuel in Parkhomov's 225-day reactor? Is that why, with an electric discharge in the 1980s or early 1990s, that David Hudson saw his thumb-sized electrode disappear? Is that why we see tungsten disappear in our Vega reactors? Is this why there was a tungsten explosion in the 1990s by Mizuno? Is this why Sapphire Group have observed a Langmuir probe of tungsten basically vanish? Because you are getting dark hydrogen or itonic clusters stimulating the decay, because the binding energy is higher and interacts with matter, causing novel nuclear reactions. And one of them is the stimulated cluster decay of 4-helium. I said to my friends, my colleagues in the MFMP, guys, I'm living on one of the largest deposits of monazite in the world, in Kerala, where I was living in India. This was back in 2013, I think. 2012 maybe, right at the beginning, maybe 2013. I said, can't we just get our reactor, our nickel hydrogen reactor, and put it inside just a brick that's literally cut out of the ground of monazite, and we put it in, and stuff that comes out interacts with the monazite and produces excess heat? That was my premonition in the first few months of the MFMP, and I believe that would work. Why? Because all of those elements in the lanthanides are there, and they all like falling apart. Look, so let's look at I don't know, what do we want? Lanthanum. Okay, not lanthanum or cerium. Praseodymium. Praseodymium, not so interesting. Let's look at, hold on, you can't see what I'm pointing at. Neodymium. Neodymium, what do we have? We have an alpha decay there, right? What do we have down here? Promethium. No, I think it's unstable, isn't it, or something. Samarium. Okay, so I've already identified 25% of samarium. I believe that this kind of thing, where he was loading and deloading and loading and deloading with deuterium, the samarium cobalt, whilst it was at elevated temperature, it was doing exactly what our copper nickel wire was doing in the Chelani wire replication in October 2013. That it was, as the fresh hydrogen was coming in, it was lowering below the Curie point, and probably even below the Debye level. And as the wire electrically heated up again, it disassociated the hydrogen, it bound to the top there, everything's raising at the same temperature, it went through the Curie temperature, and poof, you get another burst of this dark hydrogen or coherent matter coming out and going out through the gas at 3 bar hydrogen, through the borosilicate glass, through the air, through the plastic, through the metal outside of the Geiger-Müller tube, and ionizing that gas in a whatever way it was doing it. Okay, so samarium. What have we got down here? Europium. Europium has 47.82% as an alpha nuclei, decay nuclei. Gadolinium, we've got this one here, which I although small, I think it signifies a very big potential yield. Terbium. Terbium, not so good. Dysprosium. No, so On a hunch, I actually bought some europium. Actually, it's a europium salt for phosphor. And I bought this for Alan 3 years ago. And I said, can we not just run a nickel hydrogen reactor and put this europium next to it and see if we get extra excess heat? Well, now you know why. It was a hunch back in 2012-13. And it then became like the evidence started piling, it started piling in. And I had in the back of my mind that samarium cobalt story from, ICCF 6 or whenever it was, the one that was in Hawaii. But here we go, 47.8%. So, Alan, please get your europium and get it into your a nickel hydrogen reactor. And here where we have this samarium with 25%. So I would suggest taking your samarium cobalt magnet, cycling it with deuterium around the Curie point of nickel. Of course, cobalt is highest Curie point. So have we got Curie point in here? I'm sure I asked for that at some point. Now maybe I haven't. So let's put the Curie point here. Let's see, Curie. Curie point. Here we go. Curie temperature. There we go. Curie temperature. Where's nickel? Cobalt rather. 1,130 degrees centigrade. I mean, the beauty of nickel is it's so low, but it's high enough that you can, reasonably get everything at the same temperature before you go through the Curie point. Iron, you need to work a bit harder. But the point is, using nickel, you can only get the water temperature at a kind of round about this temperature, can't you? Well, whereas with cobalt, you could go quite a lot higher. So there's a lot of potential to go, to get things at the same temperature. Anyway, the point is, cobalt, I believe, samarium cobalt magnets are a very good idea to work with. If you look at gadolinium here, it's 19 degrees, so you can practically do it at room temperature. There's something for you. You can do it at room temperature. Wow, 19 degrees. I mean, you'd have to actually do some cooling. Chromium oxide. There we go. Okay, all right. Now, yeah, look at the nickel oxides here. Iron oxide. Now, it's interesting. And so I'm going to throw another one in here. Homlid is taking deuterium and he's putting deuterium over a dehydrogenating catalyst. And it's made of an iron oxides, but it also has potassium in there. Okay, and potassium is something that has a low work function, which means it will release electrons. Okay, it also has the ability with its potassium 40 to release this 1.551 million electron volt if it gets interacted with by a cold neutrino. So he passes the deuterium over and he supposedly synthesizes this ultra dense hydrogen. Okay, but is he synthesizing the ultra dense hydrogen on that thing? Well, what is he doing? Well, if you look here at the iron oxides here, I think he has it around about 400 degrees. So this is a magnesium oxide and an iron oxide here. We're about 440 degrees here. Manganese oxide and iron, some iron oxides here. It's 300 degrees. So if you're putting cold hydrogen, deuterium, over something, and you've got it something around about 400 degrees, you're going to be causing some dissociation. It's a dehydrogenation catalyst. That's what it does. It takes the hydrogen away from other stuff. You use it in catalytic processes. And the hydrogen is then sitting on, using its magnetic dipole, on your dehydrogenation catalyst. And then you fire a laser at it. And what is the laser doing? Well, we already know from 1973 Low paper, the 1973 Low paper, that the laser will enable and help coherence. Okay? So that's one thing. Plus, the laser pulse is doing what Piantelli said you needed to do, which was go through go through the Curie point as fast as you possibly can. But actually, it might just be exciting the local gas to leave instantaneously, because it's a laser pulse. It's going like that, knocking them all off at exactly the same temperature. And they are doing what I am suggesting is occurring when you do that in the reactor of whoever. Because when we did our GS 5.2, that's precisely what we did. We took Piantelli's advice, we learned from our own experience, and we combined in what we'd learned from Parkhomov at that time. And we went up and down below the Curie point. Going above and as much as possible we can above the Debye temperature. That is when the atoms are moving as much as they possibly can. And then we held, and we held. This is what Piantelli told us to do. We held. That is getting all of those electrons and all of those protons there at exactly the same temperature. And then he said, as fast as you can, go through the Curie point. Now, if we did the same thing, and then we fired a laser pulse at part of our adsorbed hydrogen on nickel, or whatever other magnetic element we choose, gadolinium, samarium, cobalt, whatever, iron, we hit it with a laser pulse, then instantaneously it would come off. There's a better chance of them being in phase because the laser pulse is very discrete. You can produce extremely short laser pulses. And so it would come off and you would produce maybe this Baruch atom, whatever. It's producing strange radiation, because you know what? Sven Olesson from Iceland, he has seen what looks like, and I've shared this, strange radiation tracks. Okay, so I think probably I've spelt it out to Piantelli. I don't know whether he heard me the day after the conference. I've given some little more detail here about the importance of using it. I was going to do a separate presentation called Slingshot on this subject, and probably I will do that. And I want to show with my physical practical experiment, which I've got all the bits, and I actually bought them, oh God, 2 years ago, or maybe 3 years ago. They're all in the other room. It's just terrible. But I've had to go through a series of things to get to a point where you can just get it. I hope people can just see that that's what's going on. And understanding how all of these things together, it doesn't matter whether it's Mills, it's Matsumoto, it's whoever. It just doesn't matter. It's all the same thing. It really is all the same thing. So our observations in 2013 and 2015 and 16, the work of Homlid, I believe it's all the same thing. Okay. So, Magic Sound. Oh, it's good to have you, Magic Sound. In one glow stick test, I drove the Cantal heater at 20 kilohertz, 800 watts. No excess heat was seen. Dog ran away moaning. It's probably the sound. So Alan, you have. It's great to have you here, by the way. Alan, you have the europium as a salt. I think I bought you some samarium at the same time. Same logic. Samarium cobalt is very easy to get. You can see it here. You can see its Curie point is really rather high. So samarium cobalt magnets down here, 993. So 720 to 800 degrees centigrade here. but you have the samarium in there. So you can do high temperature cycling around this. And so I believe that you will get, and I would use deuterium gas in this instance. And I'll tell you one other thing here, and ICCF 22, I called out the people in the room, and you go and look at my presentation. I said there's some people in this room that essentially I was saying they're holding on to things, but they've had 3 years to put this into the public domain, and I don't want to have another situation where I have to wait until someone's shutting down their lab until they're willing to talk about it. Maybe they've got it in a patent, but one author claimed that they only saw a COP of 2 unless they used particular elements, and one of them was gadolinium. And you might guess from what I've already said in this presentation who that is. So Alan, you have everything you need already in place to test what I'm talking to you about. I believe that maybe you could even take your LEC and consider putting in deuterium in there, and also consider putting in europium, and maybe you will get a better yield. But I do believe that you need to get proper Lena, you will need to be going through this Curie point of your iron here, 770, and in the same way that we did in GS 5.2, going through the Curie point here. This is absolutely critical. And by the way, once you have formed these materials, as I said earlier in the presentation, they persist in the metal, and they can continue to perform the nuclear transmutation function. They just continue to do it. And so that is, I mean, Parkhomov's 225-day reactor protocol built on our GS 5.2 protocol. So, and it was one of the most satisfying things to see. We learned from him. So we learned from Piantelli, we learned from him. We put it into a protocol, and then he learned from us, and we learned from him again. That's how it should work in an open space. Parkhomov's reactor, I believe, most of the energy was coming from the tungsten, and I believe that is because the tungsten here has this alpha nuclei that can decay. So where are we? Tungsten. Somewhere down here. There we go. So you can have this alpha decay here, but it is only a small amount. And I think part of why tungsten is good at decaying in this way is that it has is highly electrically conductive in a way that many of the other elements aren't. But you might not want all the energy to come off quite so quickly as it did. In Parkhomov's reactor, the nickel all melted down because the reactor was over 1700 degrees. But he did the protocol that synthesized the itonic clusters, the micro ball lightning, the Baruch atom clusters, whatever you like to call it, the EVOs. And they are able to sit in the metal, and you keep energizing them, keep feeding them electrons, and they will do the work. Orid diamondiferous. I kind of like it that way. I want the information to be out there, but not in a way that scares certain people. So I'm not so fussed about not so many people here. So I have around 0.5 gram of the samarium salt, not enough for a LEC test, but it could go. Yeah, I think a glow stick, but it's the europium salt I'm more interested in. I think you might be referring to the europium. I think in the case of the samarium cobalt, I now have given you, in my view, a watertight explanation for how that work in that person that was cycling deuterium in hot crushed samarium cobalt reactor. Yeah, I think it was ICCF 5 or 6 or whatever the one was that was in Hawaii. Maybe I can look up on Lenacana and maybe there's an account of that. ICCF Hawaii. Uh, ICCF Alliance. I don't know. It's ICCF 4. Yeah. ICCF 4. Okay. So ICCF 4. And maybe I can look up on lenacana.org. Samarium Cobalt. Samarium Cobalt. So Samarium Cobalt. No. No, there's nothing there. Samarium Cobalt. Talk amongst yourselves. ICCF 4 for Hawaii. Samarium Cobalts. No. Maybe I can say Samarium Cobalt Cold Fusion. That's probably what it was called back then. Okay. I think someone can dig up that. That's another thing for someone to look for. The Samarium Cobalt experiment that was conducted outside of the ICCF4, it would seem, in Hawaii, and whoever was doing that. Okay, so WP for Truth. Hey Bob, I'm just about finished shielding 1-inch glass, stainless steel, aluminium and glass under vacuum. Will it be safe? Sorry, 1-inch glass, stainless steel, aluminium and the glass is under vacuum. Whatever you're doing, I don't know the specifics of your experiment, but get yourself as far away from it as possible and find somewhere remotely monitoring it with a camera and so forth. If you can and you have sheets of aluminium and so forth, I would have the sheets of aluminium and the polymer, sheets of aluminium polymer, and then behind that some magnetic vinyl, nothing that's going to be at a distance that would burn. And ideally you would have the aluminium with a high negative potential in it, but that has its own risks. Distance is the best way. That's what Parkhomov uses, and he's still around, and I think he's 75 now, so you know. Personally interested in solid state and plasma contained energy releases through this nanofoam, solid matrices and magnetic bottle Lockheed and toroidal containment. I think we're going to show the direct electricity generation and the method behind that, and that will lead into propulsion as well, and everything will be very obvious and logical to people, especially with some of the presentations that I've done over the last several months, to understand exactly what's going on, and I will show with other visual analogs using hydrodynamics how this is working. I might even have some footage from tests done on the International Space Station that are appropriate to making it very clear what's going on. Let's deal with propulsion in underwater, in the air and in space and at any point in the universe, including unlimited energy first, before we start dealing with healing the masses. But yes. So I'm just reading any questions that people have. For those people that are watching the YouTube stream and wondering why there's a pause right now, it's because there's some really nice conversation going on in the top chat, and the top chat is able to be replayed after the the presentation is over. So if you're reviewing this later, it's well worth spending a bit of time and going and see what people are talking about, because they're having some quite good technical discussions, and like I say, it's worth knowing what they're saying. So David Butlier, what if you held it close to the Curie and hit it with sound? Yes. In fact, if you go to Piantelli's patents, he suggests one of the methods for triggering the effect is to hit it with a pulse of pressure or shock, which effectively is some sort of phonons or sound. And so basically anything that's going to cause those adhered atoms to come off, you know, as they move through the sea of electrons, they're going to form potentially these Baru atoms. We know from our own research they form, in my view, this strange radiation that we detected in October 2013, and that was observed by Francesco Celani 7 and a bit meters away from Rossi's initial public demonstration of the original ECAT, where Celani had two scintillators, battery operated, and just a few seconds before Rossi came out and said the reaction has started, they both went full scale for a number of seconds, and I believe that was a huge burst of strange radiation in exactly the same way, or dark hydrogen clusters, or these magnetic monopoles, or whatever you like to refer them to them as is observed every single time when we loaded extra hydrogen into the Constantan wire and took it, in my view, below the Curie point, and then flash went through the Curie point. I believe that is what is being observed by Zatelepin and Baranov when they're using their strange radiation detector. And I've talked about that in previous presentations. So the samarium cobalt Curie temperature is 993 to 1073 Kelvin. So it's 720 to 800 Kelvin. So it's less precisely known than iron. I like iron. If we go back to that, I like iron because it's cheap, and I like it because it has a very, very well-known Curie temperature. That's one of the reasons I like nickel and I like cobalt. These ferromagnetic single element ferromagnetic materials, and also gadolinium, but gadolinium's 19 degrees, so you've got to work in a cold environment. This is perfect for maybe cold fusion that's really cold. in say the problem with 19 degrees is that if you have a block of material, firstly, your gadolinium is going to be way more expensive. But if you had a block of material and you're in an environment that you might likely to be in, you're likely to have temperature differentials over that that are going to be difficult to get rid of. Whereas when because your environment's around that temperature anyway, when you're working at temperatures like cobalt, 1130 degrees centigrade, your Stefan Boltzmann laws means that the temperature is lost, so you have to maintain it at that temperature. So it's easy to get all of the material inside, say, a heater element to be exactly the same temperature, and then you could maybe, like I say, use laser pulses or shockwave, as is in the Piantelli patents, or sound or pressure pulse to trigger the release of the material. And a pressure pulse, what do I mean by that? I don't necessarily mean a lowering of pressure. If you increase pressure, PV equals nRT, the temperature goes up, and you only need to just tip it over, push it off the cliff to get it past that temperature. A laser pulse is very precise, and that might produce very controlled production in the same way that Homlid is doing. And I believe it's exactly the same process that Homlid is doing, because he's using this dehydrogenation catalyst, and it probably with potassium in there. Whatever the potassium salt is, it's around the temperature that he's operating at, and so it's synthesizing this ultra dense hydrogen, and when you hit it with a laser pulse, you're potentially creating these baryt atoms which synthesize the very stable what Mills calls hydrinos, but in my view this structure is not a hydrino structure. It has a smaller electron distance or whatever, and but it's not a hydrino structure. But it is magnetic and it can form strings, and you observe these strings being produced in the plasma flow discharge work of Baron. What's his name? Oh God, now I'm getting tired. The guy at the Kurchatov Institute, where he's doing you observe these ball lightning moving around 2 days, or the toroids moving around 2 days after the experiment. And that's another case of it working very stably. So you can imagine these things as being a toroidal structure, or being able to form toroidal structures and then being able to cluster fractally. And so it kind of makes sense, really. Okay, so yeah, I wouldn't. I mean, gadolinium works, in my view, in this particular experiment as work because of the alpha decay, and because it's magnetic, and also because it's neutral. So I talked to this guy about neutron absorbers, and I spoke to Alan about this contemporaneously. And the reason I chose gadolinium is because it has this unimaginably high bonds, and that's one of the reasons why I chose indium, because indium also interacts with neutrons. And if these are neutral structures, and these are kind of neutrons, these are kind of neutrons, okay, and dineutrons are neutrons, okay, they just have this ridiculously high binding energy, allowing potentially novel nuclear reactions. So if you have this type of neutrons, dineutron, and you have this type of dineutron, then what I was observing was something where neutrons may be important. Neutron absorbers, or things that I can interact with, have a good cross section for neutrons, might be important. So I was talking about that, and they said, oh yeah, well, I use those things in my experiments, and if I don't use those things, I only get a COP about 1 to 2, and if I do use those things, like gadolinium, I get a COP of 10. Project Thor's space weapon uses tungsten rods as kinetic weapon. Yeah, well, you can fire them down from space, but another way to do it is to get your tungsten, put it in an exotic vacuum object, shield its mass and inertia, speed it up to the 1/10 the speed of light, and as Ken Shoulders says, you just give it enough energy so it falls apart at its target when it enters the target, and then you have something that is 1/10 the speed of light. You never see it, and when it hits its target, it packs the punch of however many atoms of tungsten that are in there, traveling at 1/10 the speed of light. Okay, Alan, if you want some clarifications on anything I've said today, so that we can get the protocol right, it's been a long time trying these experiments, or wanting to try these experiments, but I think the time has been well spent in being able to get to a point where the clarity of understanding the process is absolutely consistent across all major linear experimental observations that I can recall, spanning back to probably the work of Lowe and Collock in 1973, basically. Okay, so Gordon's talking about the 750,000 atmospheres. So someone asked me a question about can any of this technology lead to, maybe some ways of splitting water, because we need some good news. And I said, well, after I suggested that it looks like we are producing in the Vega experiment, Henk's Vega experiment, these what I believe are cores from ball lightning. Certainly they seem to be synthesized in multiple places in the Vega channels, and you can see that they are fairly consistent or quantized sizes. We've certainly got two that are identical sizes, and they appear to have this FeO2 nature. And if you recall, prior to that, we saw that in fact, I'm going to bring up that presentation. It's probably a good way to close out, actually, because I do need to get going. But I did want to talk about this today. So let me bring up that particular series of images. Okay, so I think probably this is the best slide to start with. If you recall, what I said was, this is our magnetic core 01, and what I said was that this seemed really, really odd to me for a number of reasons. One was it was very bright, and typically something very bright is something that charges. So that would be something like silicon dioxide or some ceramic. But then it's on what we know is almost entirely copper, or copper and zinc, because it's brass and oxides thereof. And so you would expect it, if it's very bright and it's not charging, that it would be a heavier element. So is this a very heavy element? The other thing that was curious about it was that it seemed to be sucking the light out of the room. Now, normally when you get a charged object, you would end up with bands going across. So you've got the electron gun coming over from the left here, and it hits your sample, and it absorbs all those electrons on the surface, and you end up with this band around here. But you're not seeing that. You're seeing it consistently around it, and also this kind of atmosphere around it. And you can see it here, this atmosphere here, even closer. Even more clearly defined. So it suggested to me that this was sucking the electrons out of the room. And when we looked at this closer, we found that it had this basically this FeO2 ratio, because of all the other isotopes have got lower, all the other elements have got a lower oxidation state, and they're very, very low ratio on here. And in fact, there's a couple of specs on there which probably account for these bits. So really, it does look, given that is at 2.18, the Fe to O ratio, and given the fact there's almost nothing left, and they probably are in these spots, then it could be this FeO2 material. And then in the center here, 3, it's a much lower ratio. It's almost like around the outside, but not on the pole. You have this FeO2. So my point being is that the combination of this and this, I was saying that it looks like it's sucking the electrons out of the room, and possibly this could dissociate hydrogen. Now, I've got three reasons for saying that. One, Francesco Celani said that his constantan wires, his treated constantan wires, where he's doing these electric pulses and comes off, and pulses and comes off, it's an oxide of of copper and nickel, essentially, that these can at the temperature of your fingers, like at body temperature, it can disassociate water, and that is a whole other potential application for it. And then a number of years later from that, there was a suggestion that the nickel, I think it's actually nickel oxide nanoparticles, were able to, with sunlight, disassociate water. And I'm thinking that's just unfair that Chelani didn't go and publish that, and you know, now MIT are claiming essentially the same observation. And after I present, so when I was reviewing these slides here and talking about this here, I was suggesting if this is really sucking electrons from the environment, maybe it has an ability to grab those electrons more than anything around it. And could that dissociate water? Okay, well, someone wrote to me and said that there's this I haven't got the thing queued up for you, but they said that there's this guy in Japan and he's got these patents applied for where he's increased using alkali metal dopants. He's been able to create higher oxidation states than magnetite, Fe2O3, which was the highest known oxidation state of iron until this FeO2 was discovered by 750,000 atmospheres between two diamond anvils and over 1,800 degrees Kelvin, and published in 2016. He's found that these high oxidation states, which are not 1 to 2, but lower, but higher than Fe2O3, he's found that those will disassociate, or he claims in his patents that those will disassociate hydrogen at room temperature. Okay, now we are seeing this, and we saw it also here. And so we've seen it multiple times on the same sample. So we know that we can synthesize these things. Now, the question being is, if we could synthesize millions of these, you could have this material that you just put in water and it keeps producing oxygen and hydrogen. And maybe that's why some electrolyzers become more efficient over time, because maybe they are producing something like this on the surface. And since we know vibration leads to these kind of structures here because of our ultra experiments, that's what's happening in, for instance, a brown gas device or a Stanley Meyer device. Are they producing these microspheres, which are high oxidation states of iron, that are then going on to stimulate the lower energy production of dissociation of water? So if I was to do a research program, I would try and produce thousands of these. In fact, it would be nice, Henk, if we can do it, to produce a few hundred of these, maybe. I think there's probably, well, we know there's, I think I've identified on there's at least 15, 20, maybe. But we need to have more time on an SEM to do an assay. But if we could produce, say, 100 of them and we put them in a little test tube and we see if we can dissociate water with it, that would be just amazing. It would just be amazing. And is it, again, because of binding energy? Is it because, if we go back to the binding energy that we started on, and like I say, this is my round trip for the presentation. We're not looking at the nuclear reaction here. We're looking at the binding energy of bond dissociation. Bond energy, a bond dissociation, now I'm measuring the binding energy between the atoms in a chemical bond. It is the energy required to disassemble a molecule into its constituent atoms. Now I'm looking at I want ionization energy, that's what I want. Electron binding, ionization energy, that's what I want. So we're looking at cesium here is 3.839, and in fact you don't need to go much higher than that to get it off, say, something like potassium. So if we go to P table here, I'm going to go to P table, and we go to down to properties, and we go to binding, ionization, first ionization energy here. And we've got cesium, which we know is the lowest, so that is EV. That's 3.894 for cesium. But if we go to potassium, it's only 4.341. Okay, rubidium's a little bit lower, cesium's the lowest. In fact, you can see it here. Well, yeah, cesium's the lowest in the periodic table, and you're not going to get it off helium very easily. That's 24.47. So if you had some potassium salts in your water, or maybe even some sodium salts, but potassium salts I would suggest, or cesium salts ideally, you might even be able to dissociate that water or get electrons from that material fairly readily. But in terms of dissociating the water, if you grab the electrons, you might be able to split the water. Maybe that's what's going on. Maybe the binding energy of this or its desire for electrons is so strong in these things. It's sucking the electrons from the room, from this electron gun. And is it good enough to do what that Japanese person is doing, but do it better? And can we dissociate hydrogen? So that's a research program I'd like to do as well with Hank. Is there a way of making a hydrosonic pump safe? I don't think there is. No, I don't think so. If you want to kill yourself, it's the best way to do it. So the iron peroxide catalyzes the water dissociation by pulling energy from heat in the water. Yes, it's part doing that and part just wanting the electrons more. And so that it's using a combination of the thermal energy and in the case, I mean, you could probably use like maybe UV light, and I would suggest probably, if I've got it here, and that's not a red one, probably no. What have we got here? That's the green one. This so-called UV light here, this one here. Oh, damaged my camera. There we go. It's kind of like violet, but not very. Or even just an ultraviolet lamp would probably do it. In fact, Homlid, I think, says that if you use a UV light, it stimulates the production as well. So maybe a low-powered laser like that. I don't know what that was, but I don't think it would need a lot. This is 70 milliwatts, 70 thousandths of a watt. I think that would probably enough on some of these iron balls to maybe disassociate the water. And so when I've done an assay on the Vega Valley, I intend to get a powerful magnet and see if I can extract these things. And maybe there's 4 or 5, and we can do a basic capillary test maybe by inserting them into the tube. I don't know. It doesn't need a lot to prove the principle. And then since we know how we can make them, and because they're highly magnetic, we should be able to collect them. We could maybe hydrogen dissociation like that, and you could have a combined fuel cell. You could have a fuel cell over here, and the hydrogen generator, which just needs to be exposed to daylight or possibly just warmth. Like I say, this Japanese patent claimant is saying that it just needs to be at room temperature. He's not suggesting that you need light. Whereas in Chelani's claim to me, he says you need it in body temperature. You need to put the wire between your fingers, and so that's at 37 point whatever degrees centigrade. And in the MIT, they're exposing it to sunlight. Now, sunlight can obviously get to quite a high temperature, but sunlight's got UV in it. And I suspect that it's the UV because the UV can have into the several EVs. And what you're doing is you're just trying to push it over the edge. So the catalyst is doing something to make it easier, and then you're just giving it the required little bit of extra energy to push it over the edge. No. I mean, what's happening with this? The way they create this so-called blue laser, which is actually more purple, and you can look at the spectrum from the analysis I did of it. They actually have this in the infrared, and they double pump the frequency to make it into the purple. Could you use a commercial sourced powder instead? There is no high oxidation state that you can get commercially than Fe2O3. There we go. This guy is claiming by doping it with... So he, in my view, he's effectively making a dehydrogenation catalyst, which is exactly what Homlid is using. And I am suggesting that what you are looking at on the screen here, potentially, is the best dehydrogenation catalyst that has ever existed. And by the way, if this is the core of ball lightning, you can kind of get an understanding of kind of how, in some respects, it may be working. Yeah, UV light or small black light, yeah. That's kind of what I'm saying. So Homlid is saying that he can stimulate the production of ultra-dense hydrogen with a laser or a UV light. So the work is already done, by the way. And he is using a alkaline metal doped metal oxide. That is the dehydrogenation catalyst. That is what it is. Alan, you have some. You have some. In fact, I have some. You gave me some. I actually have some. You just put the deuterium gas over that, and you hit it with the the laser, and you're creating this stuff. And I believe that I've explained what is exactly going on exactly, and it's the same as all other LENR that works. How is oxygen ratio that high possible? It's a different phase of iron and oxygen. I've talked about it in a previous presentation. You can go and look at the papers that look at that. But go and look up FeO2 and you'll find that the Department of Energy are very, very, very excited about it. And I think I've just told you why. So, David, actually, I do not know whether this will work, but I suggested it might work because of the MIT work and because of Celani's work. But like I say, MIT required sunlight. We know that's got a UV component, so that is a relatively high EV photon source. And in the case of Celani, he was above room temperature. He was at body temperature. The claimant from Japan is claiming using something that is largely similar to the dehydrogenation catalyst that's used by Homlid, that he is getting an effective oxidation state that's higher than Fe2O3, and that this at room temperature, I need to go and look at that patent, but at room temperature he's claiming that this disassociates water. I'm suggesting that potentially these FeO2, if that's what they are, spheres that has been synthesized in the reactors of the Vega reactor could do this. Now, the interesting thing is the less pure structures that look nearly identical in the ultra experiments, are they also capable of doing this? I don't know. But of course, they're a lot easier to produce. You could just keep running sheets of aluminium through and collect. Maybe you could collect a few hundred of them and you could test it in the way that I've just described. And that would be a faster way. But when we look at those oxidation states, I think because the Vega experiment is low pressure and it's a plasma state, the iron-rich crenellated spheres don't have so much other elements to play with and to mess it all up. It's a more pure environment. You've got the thing in the middle. It's basically rebirthing matter, and it's producing this core which is very pure. And in fact, there might be another paper I want to talk about. Do I want to talk about that? No, I'm going to do that another one, but it is about FeO and nuclear synthesis. So I think that's the next presentation I'm going to do. It will be following off this FeO2, the ratio between iron and oxygen, but in the sun. And it will be talking about the fact that we know you do not need a Big Bang to synthesize all of the elements on Earth. These elements can be produced on Earth. We can produce them. It's already been done. I've discussed it, and it already goes on in the sun. And I'm going to refer to other data from the Parkhomov 225-day reactor to support that, as well as this paper from a long-term, very senior scientist at NASA. Thank you, Ether222. Well, temperature radiates infrared at RT. If multiple infrared photons absorbed and used by catalyst, then lots of energy available to split water using single bath temperature. Right, okay. Okay, yeah, okay, fine. Yeah, got you. Jason, we're working on it. Okay, it's 1:19 here. I think I probably said enough. This was meant to be a short presentation with a technical test at the beginning. Thank you for those that were able to help me with the technical test. I pretty much know what I need to do tomorrow. I may call on someone to help me with a technical test, but to close out, this was, if I can find it, this was binding energy, technicalities, and a technical test. So I did a technical test, but I suggested several technical tests. I suggested the outline of why I spoke to Francesco Celani after Azizi and said, look, this is how it's working in my view for your type of system, and the evidence is just overwhelming now, and it's all the same thing. And I've given more details as to the thinking behind what I said to Francesco Celani in this presentation, and I encourage you to go back and listen to it and ask me questions on remoteview.icu under this binding energy, technicalities, and a technical test, so that we can walk through it. But essentially, I believe that I've carefully argued why we're seeing helium wanting to come out, carbon and oxygen, and then I've explained iron and nickel's role, and the fact that iron, I believe, is absolutely critical, as was identified by the Russians in their declassified 1992 CIA document, where they said that we can get to Alpha Centauri in back using the energy that's within 1 kilo of iron in 12 years, and the way you remove the energy from the iron also is the propulsion. And we will walk through how that is occurring in my view, and I think it will be so clear, and you'll be like me, you don't really know which way to go first to enjoy developing this technology, but we really are on the dawn of an old age, and I thank everyone that's been able to help support this project, the work of Alan Goldwater especially. Dave and Henk this year has been absolutely amazing, and into last year as well, and people like Roy Shinamaza, and thanks to Sho and to Charlie and to Charlie and to all the people like Lion. If it wasn't for Lion, many of these things would never have been possible, and to Matsumoto for sharing his book and the insights that gave, and the clarity and the support for observations that we had already shared and other ones that have come since, and to Suhas Ralkar, because if I hadn't seen something in his lab in my very first visit there, the understanding of how the propulsion works would not be so clear, and I would not be able to describe that to you in the coming weeks and months with such clarity as you're just going to go, yeah, that's how it works. Yep, okay, done. But we will be able to travel to the stars. The propulsion is just amazing, just amazing. As Ken Shoulders said, it's like it does that very nicely. And then the transmutation is so efficient, he said. It's transmuting it to elements and transmuting it back, and that is what it's doing. And it all comes down to getting coherence, and that is it. That is exactly what Homlid is doing. That is exactly what was suggested in 2001 by Matsumoto, and that is exactly what is happening in the work of Piantelli and all nickel hydrogen systems, blah, 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 blah. All right, so thank you very much for your time, and I will see you in the next video. So it's been, I didn't really set out to say the things that I said tonight. I wanted to put them in a more structured presentation. I hope you got the point. But I think we really are on the dawn of an old age. Bye-bye for now.